just going to start it now, and um, I won't have the previous part that we just did recorded, but that'll be okay. Okay, so here is my reaction, or my problem that I want to solve. I've got a pencil that has a mass of 5 grams. It's standing on the point. If the point has a radius of 0.1 millimeters, calculate the pressure the pencil exerts on the tabletop in pascals. This would give us a workout in using these. So let's think about pressure is force over area, and a Pascal is a Newton per square meter. Those are the definitions. Force of gravity is mass times the gravitational constant. And so we've got a mass. That's going to be, it's 5 grams, so it's 5 times 10 to the negative third kilograms. Remember, when we calculate mass now, in any formula, we have to put the value in kilograms, not grams. The SI unit for mass is kilograms. Now, the gravitational force then is going to be 5.00 times 10 to the negative third power times the gravitational constant is 9.087. So what I'm getting for the gravitational force acting down on that pencil is 4.904 times 10 to the negative 2 newtons. Now, area is pi r squared. So pi is 3.14. The point was 0.1 millimeters squared. So we've got some units to take care of. We've got to get rid of millimeters squared and go to meters squared. Remember, area has to be length times length, and that would be length squared, and length has to be meters. So area has to be expressed in square meters. So if I do this math, that will convert to square meters. Okay, I'm getting 3.142 times 10 to the negative 8 square meters of area. Now we're ready to calculate the pressure. The pressure was 4.09 times 10 to the negative 2, 4.904, I'm sorry, times 10 to the negative 2 newtons from right up here, divided by the area that we just calculated, 3.142 times 10 to the negative 8 square meters. And so when I do the math, I get 1.56 times 10 to the 6 pascals. That would be 229 pounds per square inch in our familiar English units. Now, do you understand why when you drop a pencil, it always breaks the lead? I see why. Okay. Now, let's look at another problem. We got 9.63 gram sample of carbon dioxide trapped in a piston that initially has a volume of 3.50 liters. When the pressure is 155 kilopascals and the temperature is 25 degrees, what force must be exerted on the piston if the area is to be 100 square centimeters in order to reduce the volume to 1 liter if the temperature doesn't change? Awful wordy, but we can put all the things together. Okay, to determine the force, we need the pressure in the area. So I want you to kind of watch and see the method I use to solve problems rather than the solution to this particular problem. What I'm going to always do is I'm going to look at the problem and I'm going to determine what I need to know. And I need to know the force. To get the force, I'm going to need the pressure in the area. So this is going to be a Boyle's law problem because the temperature is constant. So the initial pressure times the initial volume has to equal final pressure times the final volume. And so my pressure final pressure is going to be 155 kilopascals there. The volume is going to be 3.5 liters divided by 1 liter. So this times this is equal to this. I can solve for that. And I get the final pressure needs to be 542.5 kilopascals. Now, force is, per unit area, force divided by area then will be the pressure. The area is 100 square centimeters. I've got to put that into meters. Don't forget this step. This is critical. You have to go to SI units, and the SI unit for mass is kilograms, and the SI unit for distance is meters. So area has to be in square meters. So I've got to do this math, and I come up with 0.01 square meters. And of course, there are more significant figures, but we'll deal with that later when we have to. So the force is going to be, the pressure we got up here was 542. Now, notice we need to get rid of that kilopascal here. It's pascals per square meter. And the way we convert within the metric system is just replace the prefix with what it's equal to. So we've got a kilo there, that's 10 to the third. So 542.5 times 10 to the third Newton per square meter times 0.01 square meters would give us the force that we have to have. The force is going to be 5.42 times 10 to the third newtons. So this would give us the answer to this particular problem. To what temperature must sample in number 2 be cooled to affect the same volume change if the pressure is held constant? Okay, again, it's a Charles law problem. So V1 over T1 equals V2 over T2. That's the relationship. So we analyze the problem, discover the relationships we need. Now we plug in what we know and solve for anything we can. So these are the things we know from the problem up there. The thing I don't know is T2. So I can solve for that. And that's going to be our answer. It's 85.2 kelvins. That's minus 188 degrees Celsius. So that temperature would have to be cooled a lot to affect the same change that we talked about in the previous problem. And this is for an ideal gas. It's not going to work for carbon dioxide. You know why? Because CO2 freezes at minus 56 degrees Celsius. It's not going to be a gas at minus 188. So this, I wanted to do it this way so you could see we can calculate a number that obeys all of these laws, but the gas we're dealing with might not be ideal. And if it's not ideal, the answers we get are not going to be, they may be correct for the problem, but they're not going to be realistic to the world we actually live in. What mass of carbon dioxide must be added to the above piston in order for the volume to remain at 3.5 liters if the pressure is increased to the answer that we got in number 2 earlier? I'm sorry, I haven't shown you my screen, so let's pull that back up so you can see it as I work through the problem. You remember now, you can download these PowerPoints from D2L and follow them at your leisure. Okay, what mass of carbon dioxide must be added to the above piston in order that the volume remain at 3.50 liters if the pressure is increased to the answer we had in number 2 and the temperature is reduced to the answer we got in number 3? Okay. We've got a combined gas law problem now. The combined gas law can be expressed like this. Ideal gas law is PV equals nRT. So if we solve across for R, P times V over N and T would be equal to the ideal gas constant. That's a number, 0.0821. And it doesn't matter what the individual values are. When you do this math, you're going to get 0.0821 liter atmospheres per mole per Kelvin. Now, that means that if you have some other conditions, that would also be true. So I can treat one side of this like initial conditions and the other side like final conditions. So these are my relationships. And now, these are the data. I've got 155 kilopascals for the pressure. I've got the number of moles is 0.219, and I've got the temperature to be 298 degrees Kelvin. Okay, now the volume is constant, so the volume will cancel out both sides up there. So the pressure over P1 over N1 and T1 will equal to P2 divided by the number of moles. In the second step, we're going to add some moles to it. I don't know what it is, but this is the temperature we got for the second step. Now, be sure your units are in agreement. This is kilopascals over here. This has to be kilopascals. This is moles over here, so my X has to be in moles, and the temperature is going to be in kelvins as it is on both sides. If I solve that for X, I say that in order for us to have the conditions required in the problem, the number of moles we need to add or have in the problem is 0.373. Now we started out with 0.219, so then we can calculate the number of moles we have to add. We take the total we have minus what we had to start with, and we have 0.15 mole, 4 moles of gas would have to be added in order for this to work. That would be about 6.8 grams if it's carbon dioxide. What mass of carbon dioxide is in a balloon that has a volume of 10.5 liters when the temperature is 25 Celsius and the pressure is 1.5 atmospheres, 1.35 atmospheres. Okay, this is an ideal gas law problem. See, I've got a gas, I've got volume and temperature and pressure given, so I can solve for what I need, the number of moles. Well, there is the pressure that we had, 1.35 atmospheres. There's a volume, 10.5 liters. I need to divide that by the constant, 0.0821, and divide it by the temperature. And remember, the temperature has to be in kelvins. So I take 25 and add 273, and I get 298 kelvins. And I can now solve for that. So the number of moles is going to be 0.579 moles of carbon dioxide. But the answer needs to be in mass. So I need to do a conversion. And all I have to do is take the number of moles and multiply by the molecular weight of CO2, which is 44. And we come up with 25.5 grams of carbon dioxide. Now, what's the density of nitrogen gas at 1.25 atmospheres and 35 degrees? Well, it's an ideal gas laws problem again, but remember we're going to use the N over V is going to be P over RT, and number of moles is G over M. So G over V, when I substitute that in and solve for G over V, that's density, is PM over RT. This is a side, I'll tell you how I remember this, crazy corny joke, but the density is the knights over the round table. You'll get it, just think about it. Okay, all right, so I put in my numbers. 1.25 atmospheres. Molecular weight is 28 for nitrogen. Remember, it's diatomic. 2 times 14 gives me 28 grams per mole. And the ideal gas constant is 0.0821. And when I add 273 to 35, I get 308 degrees Kelvin. So there's my math. I come out with 1.38 grams per liter. Now, this is sort of typical of gaseous masses. Anything that's a gas is going to have a density roughly in a range like this. It's going to be from 1 to maybe 15 or so grams per liter at the very maximum. So if you come up with numbers like 135 grams per liter, it's probably wrong. Or if you come up with a density of 0.004 grams per liter, it's probably wrong. So you can get an idea of what the numbers should be. So if you put some numbers up here in the wrong unit, you'll get an answer probably that's not going to be in the range you expect for gaseous densities. You always want to check your numbers to see if they make sense. Okay, now, suppose 3 liters of ammonia gas and 5 liters of nitrogen dioxide are passed over a catalyst at 500 degrees C and 2.5 atmospheres. What volume of product gases, dinitrogen, and water vapor will form at this temperature and pressure? Now, first thing is temperature and pressure is constant. So we're going to have 500 Celsius and 2.5 atmospheres for everything. Now, this is going to be a limiting reagent problem. So we take the volume that, remember, we're going to treat these balancing coefficients as if they were liters. That's what the law of combining volume said we could do. We don't have to treat that like 8 moles. I can say 8 liters of ammonia and 6 liters of nitrogen dioxide would make 7 liters of nitrogen and 12 liters of water vapor. That would be the same for all of these. So it's a stoichiometry problem. The 3 liters given in the problem divided by the 8 liters for ammonia given in the balanced equation. That's the rebalancing factor. Also for the oxygen rebalancing factor, there's 5 liters given in the problem. The equation is showing 6 liters, so its rebalancing factor is 5 divided by 6. So it's 0.833. Comparing the 0.375 and 0.833, the 0.375 is smaller. That's the limiting reagent. Now we can get the answer by just taking that limiting reagent and multiplying it by the number of liters shown in the products. It asks for the amount of each one of them. I wanted to show you doing it this way, just so you'd understand. You don't have to do one problem and get the amount of nitrogen, and then another problem to get the amount of water. You just add these two coefficients together. The equation up here is showing 12 plus 7, 19 liters of gas. So all I got to do is multiply my rebalancing factor by 19, and I'll get the answer. 7.125 liters of product is what you would form. Now, here's a much more difficult type of problem, but it sort of puts all of this stuff together that we've been doing with gaseous stoichiometry. Copper does react, 3 moles of it, with nitric acid to 8 moles of it, HNO3 aqueous, to form 3 moles of copper 2 nitrate, CuNO3 taken twice, plus 2 NOs, plus 4 waters. Okay, so now we've got another limiting reagent problem. These are the only things that's involved in this problem. We have the copper, the nitric acid, and the nitric oxide, NO. Those are the only things that we have in this particular problem. So I can ignore the rest of the stuff in solving the problem. Let's do our rebalancing factors. Okay, I've got 1.5 grams of copper. There it is. And the equation is showing 3 moles of copper. That's 3 times 63.55 grams. So I have a rebalancing factor for it that maybe I'd calculate later. Now, we're using 10 milliliters of 6 molar nitric acid. So that's 10 milliliters times 6 moles per liter is 60 millimoles of acid that we're putting in. I divide that by the number of millimoles of nitric acid that's shown in the problem. 8 moles would be 8,000 millimoles. And so I've got two rebalancing factors. The one for copper is 0.00787. The rebalancing factor for the nitric acid is 0.00750. That's the smaller of the two. So that is the rebalancing factor that we would use in solving the problem. My answer is always the limiting reagent rebalancing factor times the equation quantity of the substance asked for in the units that's in the problem. We wanted to know what volume of the nitrogen dioxide is there. Now, you cannot put 2 liters in here. Don't do that. We have to calculate the number of moles and use the ideal gas equation to do it in this case. I did not use gas stoichiometry for the other sides of the equation. So that's why we have to do it differently here. Okay, so now I've got the number of moles of the nitric oxide I'm going to make is 0.015. I can use the ideal gas equation now to solve for the volume. It's the number of moles, 0.015, times R, 0.0821, divided by the temperature is 35 plus 273 kelvins, and divided by the pressure. The pressure is 745 torr divided by 760. 75 torr, we have to have it in atmospheres. That's what this factor does, converts to atmospheres. We got a little messy math, but you can clean it up. And if you do, you will get 0.387 liters or 387 milliliters, depending on what your unit the answer is going to be. Now here's a checkpoint on this. You should really always work these checkpoints out to be sure that that you can do them. If you have problems with them, you can email me. I would prefer that you go onto the discussion chats on D2L and talk to each other about it and see if you can come to a conclusion. So here's the checkpoint problem that you're working. You have a latex balloon has an inflated volume of 5 liters. What mass of helium is required to fill the balloon at 25 degrees and 1 atmosphere pressure? The second problem is what mass of air, average molecular weight is 29, would it take to fill the same balloon to the same volume at the same temperature and pressure? Now, believe me, this is a real easy problem. Now, aside from this, I didn't ask you to calculate it, but if you took the difference in mass between these two, between the mass of the air that's in the balloon when it's filled to that volume, and the mass of the helium when filled to that volume, and subtract them, that gives you how much that helium balloon can lift. It's kind of interesting. And then here's another one. Now this one is not easy. It looks deceptive, but I want to show you. You've got 6 grams of ammonia, 6 liters of nitrogen dioxide reacted to completion. That's going to be limiting reagent. What volume of nitrogen will form if the reaction is carried out at 740 and 37 degrees? Now I'm looking at that thinking, okay, the temperature is going to be held constant. The best thing I should do is work this as a volume to volume type problem using the law of combining volumes. If I'm going to do that, what I need to do is do a side problem where I convert 6 grams of ammonia to its equivalent volume at 37 Celsius and 740 torr. Once I get that, I'll know the volume and I know the volume of this at that pressure. Then I can do the problem easily. The other way you can do it is, okay, let's do it by mass. Well, if I'm going to do it by mass, then I have to convert this 6 liters of NO2 at 37 degrees and 740 torr into mass of NO2. And if I do that, then I can work the problem. So Usually there's a lot of people have difficulty with this one, but if you do with those hints, if you do it with those hints, you should be able to get the answer. Okay? All right. Now, we're going to probably run out of time with this one. If we do, I'm just going to keep on recording, and I'll put the recording up on D2L for you all to listen to the last half at least. I might even go back and just re-record the whole lecture and put that up for you, so we don't miss out on that first part that I forgot to start the recording on.
That would be fine, Mr. Pearson.
Yes.
Got a question. It's kind of with the lab, for your chemistry lab, as far
Yes.
as that go. I know the due date is by 5 p.m. today.
Yes.
Is that correct?
Yes.
Okay. Is there any way by chance we can have extra time because of trying to figure out the virtual lab, if possible?
I think I can still go in and move the report end date to maybe tomorrow evening, if that would help you.
Okay, that would be fine.
Okay. All right. I'll try to do that.
Around what time would that probably be?
I'll probably around 5 p.m. tomorrow. Maybe just give you an extra date.
Okay, that'd be fine.
Okay. All right.
All right, thank you.
All right. Let's continue then with this law for Dalton's law of partial pressure. It says the total pressure of a mixture of gases is the sum of the partial pressures if each were alone. Now, if you think about this, when we're talking about ideal gases, I haven't said what they were. I haven't said they're nitrogen or oxygen or carbon dioxide. It's just an ideal gas. We might have worked problems with some of those, but we use the ideal gas equation, which doesn't depend on the identity of the gas. So it doesn't make sense if I've got a mixture of gases in a container, I could just pretend I put one of them in there, measure the pressure, and then put the other one in there and measure the pressure that I put in, and the sum of the pressures would be equal to the pressure of each one individually. That makes sense. And that's all that Dalton's law says. The total pressure is just the sum of the partial pressures. Now, we do this in lab routinely. You collect the gas, and we always do that by taking a bottle and filling it with water and then bubbling the gas into the water until it fills the bottle, and we know how big the bottle is, so we know what the volume is. But the gas that's inside is not just the gas we bubbled into it. It includes the vapor pressure of water. So the total pressure that we measure in the lab inside that bottle is going to be made up of the pressure of that gas we collected plus the vapor pressure of water. And you can look that up in the back of your lab manual, get those values and subtract to get the pressure of the gas that you collected. So this is a very useful relationship. And you can just say that the partial pressure of any gas is just the number of moles times RT over V for that particular gas. Now, we're going to now rearrange this term a little bit and generate what's called Raoult's law. And it says the partial pressure of a gas in a mixture is the mole fraction of that gas times the total pressure in the gas mixture. Now again, think of the logic here. Pressure is caused by number of moles. So if I've got a container of gas that's got lots of different kinds of gases in it, the mole fraction of each one is the number of moles of that particular gas. So sure enough, you would expect if it's 60% gas 1 and the total pressure is 760, then the pressure of gas 1 would be 60%, 0.6 times the total pressure. And that's perfectly logical, and that's exactly what you see. Now, here's another useful relationship. If you've got something that is mixed in a solution even. This was essentially for gases, but if you've got some mole fraction of a gas dissolved in, or a gas over a liquid, the liquid has its own vapor pressure. Remember I told you you could look up the vapor pressure of water in the back of your lab manual? Okay, you can. And so you know what the vapor pressure of any pure substance might be. You could look that up. And then if you've got that in solution, say if I dissolve something, well, let's suppose I've dissolved sugar in water. Well, the vapor pressure of water at 25 degrees is, I'd guess about 27 torr. And the sugar doesn't have a vapor pressure. So when you measure the pressure of the water, and you got this pure pressure, and now you dump some sugar in it and measure the pressure again, that would be this pressure over here. That would be the vapor pressure of water in that mixture. And you will have reduced the molar composition of that solution from 100% water to some less than that percent of water after you've dissolved stuff in it. So I could solve for that X by just taking the ratio of these two pressures, Pi over Pi super zero. The pressure I measure in the solution divided by the pressure I measured before I put the sugar in will give me the mole fraction of water in that mixture, and I can use that to do all kinds of things. In Gen Chem 2, we'll do molecular weights this way, and this is a very useful relationship. Well, here's your checkpoint problem on that. By the way, now the time for the class is really technically over. So if you have to leave, it's certainly okay. But I will continue until I get the end of this recording. And then I'll either send it up as is, or I'll add, just do the whole thing and send that up to you. Okay, now a mixture of 5 moles of nitrogen and 8 moles of oxygen, the pressure is 760 torr. What's the partial pressure of nitrogen in the mixture? Okay, what's the partial pressure of oxygen in the mixture? Okay, these are going to be expressions of Raoult's law. You got 5 moles of nitrogen, 8 moles of oxygen. You can get the mole fraction. You're given the total pressure. This is an easy problem then from Raoult's law. Now, we're going to look at in more detail just what we mean when we say ideal gas. And this is done by what's called the kinetic molecular theory of gases. And it's composed of a few little simple assumptions. Gases consist of a large number of very small particles that are in continuous random motion. Now, how do I know that? Okay, I know that gases diffuse. So if I open a bottle of ammonia right in front of me and we were in the classroom, then the people on the front row would smell it first, and then the people in the next row, but eventually that ammonia would get out into the entire room. And so that means that when molecules of the gas are moving, they have to somehow or other make their way toward that hole, that opening, when I open the bottle. And that means that the molecules are diffusing in every direction at once because that opening could be anywhere. And the same thing would occur. The total volume of molecules in a sample of gas is insignificant compared to the volume of the container. So gases are very compressible. And we'll have a cartoon on that a little bit later. So if you compress a gas, you can imagine you're pushing the molecules closer and closer together. Ultimately, you would reach a point where the molecules would be just crammed right together for the whole container. And if you looked at the volume that you would actually have when that took place, it would be extremely small compared to the volume you started out with. So mostly there's empty space in gases. They're very far apart and moving very rapidly. That's why they're so compressible. we have to assume that there's no forces between particles of a gas. And that would be true if we looked at Boyle's law. Because if you start pushing gases close together and they become more attractive toward each other, then when you push them close together to make the pressure go up, it's not going to go up as much because the molecules are going to start sticking together because they're attracted toward each other. When you force them close enough, they would stick together. So if I had two individual molecules and I pushed them close enough and they fused together to make A2, a diatomic molecule, I would go from 2 moles all the way down to 1. And you can see that the pressure would be much, much smaller if it were 2 than if it were 1, than if it were 2. Okay. Now, the other assumption is that the collisions between the molecules and the walls and with each other are elastic. What that means is they don't lose energy when they bump into each other or get close together. Now, when they bump into each other, if they stuck together, then you see we would have the number of moles decreasing that's inside the container. So if the collisions are elastic, they're going to bounce off with the same amount of energy they had when they came together, and they can just keep on doing that forever. They can bump into each other and bump into the walls to create the pressure. As long as they don't lose any energy when they collide, that gas is going to be stable. If they lost energy on collision, the gas, any gas would, if you wait long enough, would just turn into a liquid all by itself. That doesn't happen. Okay. Now, here's one that's maybe not so easy to guess, but fairly easy to demonstrate, is that the average kinetic energy of molecules of a gas is directly proportional to the absolute temperature. Now, the truth of the matter is that's always true for gases, liquids, or solids. The only difference is gases move a lot long distances compared to their diameters before they hit each other. But and they have a kinetic energy that's relatively constant between collisions. Nothing much is going to happen. But if you bring the molecules together and put them in a liquid state, the only thing you've done, liquid at 25 degrees, the molecules are still there. They're still bumping into each other, and they're bumping into each other, bouncing around within that cavity caused by the other molecules around it. And their average kinetic energy within that cavity is still proportional to the absolute temperature. Now, in the liquid, the cavities, the molecules can actually migrate through the sample and diffuse through the whole sample. But within that cavity, they're still going to have a kinetic energy average that is proportional to the absolute temperature. Likewise, if you have a solid, the molecule itself can't get out of its lattice position. It's going to always be where it always was. And the only thing that's going to happen differently is, again, within the solid. The surrounding molecules create a cavity that any particular molecule is bouncing around within. But it can't get out of the cavity, and the cavity can't move. But the temperature, the absolute average kinetic energy for that solid is still the same at the same temperature. So think about ice and liquid water and gaseous water. If you had ice at 25 degrees, now it's hard to do that, but you could imagine you do. Suppose you had ice at 25 degrees. It would have a 3/2 RT would be its kinetic energy, be the same number as the liquid at 25 degrees, 3/2 RT, as the gas would have, 3/2 RT. So it is constant and it is independent. So this rule number 5 for the kinetic molecular theory is really universally applicable to all substances at all phases. This is, in terms of gases, this gives us Graham's law. Now, it says the kinetic energy is the same. Kinetic energy is 1/2 mv squared. And I gave you the value a while ago. It's 3/2 RT for any substance at any temperature. Now, mass is the molecular weight, and the molecular weight would be different for different gases, but different gases would travel at different velocities in order to hold this constant. Heavy molecules would travel at a lower velocity than light ones. So if you put two different gases together at the same temperature, then this is the relationship I can have. The 1/2s will cancel out. So the mass of one gas times the velocity of that gas squared would equal mass of the other gas times the velocity of that other gas squared. Or you could write it this way, which is the expression of Graham's law. Volume, a velocity of gas 1 over velocity of gas 2 is square root molecular weight of gas 2 over molecular weight of gas 1. And now there's a checkpoint on this that you would want to work as well. So here's the checkpoint. It's found in an experiment that it takes oxygen gas 5 seconds to diffuse 35 centimeters. How long would it take for sulfur dioxide to diffuse the same distance, 35 centimeters, in the same apparatus at the same temperature and pressure? You're going to do that. You're going to use Graham's law, mv1 over v2 square root m2 over m1. Okay. Now, this is also gives rise to diffusion, and it says that the flux of stuff moving from one place to another is the negative of d sub f, a diffusion coefficient, times the change of concentration on each side of the barrier it's diffusing across. By the way, this is really Fick's law, but it's the one that I've claimed a couple of times being Pearson's law of stuff. Stuff always moves from where it's concentrated, where it is, to where it's more dilute, where it's not. And this is an expression of Fick's law. Okay, I've got a little cartoon that shows you this. I've got some concentration of these little orange beads on the left side of some window area, and I've got a different concentration on the other side. And it looks like here I've got more on C1 than I have for C2. So I'm going to get a diffusion in each direction proportional to the concentration of that one. So the concentration is higher on this side, so it's going to diffuse to the right, and the second molecule is going to diffuse to the left through the opening, and the more concentrated side is going to move to the more dilute side as a net flow. And so the net flow is going to be from the more concentrated side to the more dilute side. Okay, that's my Pearson's law of stuff. Stuff goes from where it is to where it's not. And that means all kinds of stuff. It means concentration of HCl on one side of a membrane and concentration of HCl on another side of a membrane. It means gaseous CO2 and gaseous CO2. It means heat, joules of energy on one side and joules of energy on another side. Every kind of stuff follows Fick's law. You'll learn more about that in physical chemistry if you make it to that. Now, let's look at real gases. And there's lots of different ways to express real gases. We're only going to do one of them. It's called the van der Waals equation. We need to look at how real gases differ from ideal gases. Now, an ideal gas has no force between particles, and the particles have no volume. That is what we would have to have for an ideal gas. We talk about the molecule being just a point particle, no volume. Real gases do have volume, and they do have forces between them. Now, we want to choose conditions where those forces are minimal. Now, if I have a gas at high temperature, that means it's going to have a lot of kinetic energy. So when imagine two molecules touching each other, and then you pull them apart all the way to infinity, there would be a certain amount of energy required to do that. Now, if you've got a gas, so that when they come together, they have a kinetic energy higher than that amount of energy, then they're going to always bounce off each other. They're never going to stick together. So that means a real gas will behave like an ideal gas at high temperature. Now think about the forces between molecules. The further the molecules are apart, the lower the force is going to be. If I lower the pressure, the volume increases. So that means the molecules get further apart as I lower the pressure. Lowering the pressure then would cause the gas to behave ideal. So a real gas becomes an ideal gas at high temperature and low pressure. Now, what do we mean by high temperature? I mean a temperature that's much higher than the boiling point of that substance when it was a liquid. Because the further it is away from that boiling point in temperature, the more kinetic energy it's going to have above what it would take to just liquefy out and be a liquid. So high temperature just means a temperature far above that substance boiling point. And low pressure, well, typically that means pressures like an atmosphere or 2 or 3 atmospheres, but it's not going to behave as ideal gas if you get up to 1,000 atmospheres. You know, you can take graphite and put it under several thousand atmospheres of pressure and it becomes a diamond. So things change at very high temperature and pressure, low temperature and high pressure. So at high temperature, the kinetic energy of the molecules is so high that the small intermolecular forces are insignificant. So here's a little cartoon showing what I said a while ago. Imagine two molecules stuck right touching each other, and you start pulling them apart. As you pull them apart, we're going to look at what happens to the energy or the work required to do that. So as I start pulling them apart, I'll put in a certain amount of work. Pull them apart a little further, I'll put a little bit more. Now remember, as they get further and further apart, the force between them gets less, and so the amount of work gets less with each one of these movements. So what's eventually going to happen is it'll level off like this. There will be some distance that essentially, actually it doesn't get all to this line until you get to infinity, but far before you get to that, you will get 99.9% of the energy. So there is a certain fixed amount of energy it takes to separate the molecules. So that, now, if the kinetic energy is much above that limit, the gas is going to behave ideal. How can we get the kinetic energy? Remember, 3/2 RT is the kinetic energy of anything. So at high temperature, this is going to be true. At low pressure, the distance between the molecules gets smaller. So if the average distance between molecules is much bigger than the diameter of a molecule, then this will be satisfied. And we add up all of the volumes in the container. Here's a little cartoon that illustrates that. I've got some gas molecules in a container. Now I'm going to imagine compressing them down to a little layer of molecules in the bottom of the container. Well, you can see the total volume of molecules is insignificant compared to the volume of the container. So that would be a case where the gas would behave as an ideal gas. So the volume available to the gas is about the same as the volume of the container. Then I can use the ideal gas equation. So that gives us a clue of what we need to do to correct the ideal gas equation to make it work for real gases. This is called the van der Waals equation. It corrects for the intermolecular forces and the volume of molecules that our real gases have. So we need to make a pressure correction, and it's caused by collision of molecules with the container walls. That's how we get pressure. So if I'm looking at this, here's a molecule, and here are the two container walls. As the molecule hits this wall, it's going to go across over here and hit this wall and come back to its original position in the container. And the number of collisions per second that molecule does with these walls is the pressure. Now suppose I put a second molecule in the container, and let's suppose that it goes like that. We had a near miss, comes back and hits that molecule, then returns back to this wall. Now you can see it's going to make more collisions with the wall per unit time because that second pass didn't have to go all the way over to the other wall. It just went over and hit another molecule and returned to the wall. So the presence of molecular collisions in the gas itself will cause the pressure to go up. So we need to add a term to that pressure to correct for that. Now, if I've got a projectile and a whole bunch of molecules, the probability of a projectile hitting a target is going to be proportional to the concentration of targets. So that's the molar concentration, N over V. Now let's imagine the other side of a collision. Suppose I got a lot of projectiles and one target molecule. What's the probability that one of these projectiles will hit one target molecule? Well, that's proportional to the concentration of projectiles. That's going to be N over V as well. So the probability of a projectile hitting one of many targets and the probability of a number of projectiles hitting one particular target is each N over V. So both of these things have to occur for a collision to take place. So if the probability of a projectile hitting a target is N over V, and the probability of targets hitting projectiles is N over V, then the probability of a collision is the product of the two probabilities, N squared over V squared. Okay, so now I've got my correction term that I can add to the pressure part. This will take care of the fact that molecules have forces between them. Remember, forces between molecules is what causes them to collide with each other. Now let's make a correction for the volume term. Okay, that one's really easy. I've got all these molecules in the container. I compressed them down to that little layer in the bottom. So I need the volume available to this molecule in the container is going to be now, the volume it has is the volume minus the volume of these molecules. So the volume correction, the volume available is going to be V minus N, the volume of molecules. The volume of 1 mole of molecules is a value B. So the volume correction is going to be minus NB. Now, this is the ideal, the van der Waals equation, and it really, really does work well. But it has the disadvantage, it has a constant A and a constant B that have to be added. But these are values for each individual real gas molecule. If I'm talking about nitrogen N2, there is a value of A for N2 and a value of B for N2. If I'm going to talk about oxygen, I can look up a value from A for oxygen, O2, and a value of B for oxygen, O2. And I can plug the numbers in. So there is that disadvantage, is the van der Waals equation is for real gas, and you might guess each real gas has a different equation in the sense that those constants would be changed from one to another. It works even in the fluids. You can describe liquids by the van der Waals equation, believe it or not. It's really, really good. Okay. What's the pressure in a vessel? 5 grams of helium, 5 grams of argon at 1.5 liters. Okay. Both gases are ideal. Total pressure would be the sum of the partial pressures. And we've got this. And so I've got the pressure I would expect would be for the helium would be 22.1 atmospheres. For the argon, the number of moles would be this value. It would be 2.21 atmospheres. Total pressure is the sum of the partial pressures. So there's that is. Both gases are ideal. We got a Raoult's law problem. There's the values, and there's the result. What's the molecular weight of a gas? 0.22 moles of the gas. It fuses through an opening in 65.2 seconds. If the same pressure of neon is placed in the chamber, 0.35 moles diffuse at 55.3 seconds. Now, let's solve this. If we treat both gases as ideal, we can use the Graham's law relationship. And what it says is V1 over V2 is M2 over M1. Remember, it's an inverse relationship. So my velocity for my unknown is 0.22 moles in 65.2 seconds. That's 0.00337. The velocity for nitrogen is 0.35 moles in 55.3 seconds, 0.00633 meters per second is what these would be. Now, I want you to notice something. The unknown travels much slower than nitrogen does. That should tell you the molecular weight of the unknown has to be greater than neon. I said nitrogen, sorry. Okay, so I put my numbers in. Here's the molecular weight for neon. I can solve for the molecular weight of the unknown. I get 71. So I have set this up correctly because the molecular weight of 71 is greater than 20.18. We expect the light molecule to travel faster than the heavier one. Okay. How long would it take for 0.16 moles of SO2 to effuse from a chamber if it takes 35.25 seconds for 0.25 moles of N2 to effuse from the same chamber? Okay, again, this is a Graham's law problem. We can set it up just as before, except now we're solving for the velocity of the unknown, and we got this value for it in moles per second. So it should be less than that. And notice if I knew the number of moles per second and knew what it is, SO2, then I could calculate how many grams per second it happens and so forth. So the time it would take for 0.16 moles to effuse, what's given in the problem, divided by the velocity, moles are going to cancel, and the time would be 33.9 seconds. Now, that should be okay. Calculate the pressure that 50 grams of CO2 would exert in a 275 milliliter container. Use both the ideal and the van der Waals equation. Here's my data. Okay, so there's the data for everything, the number of moles, the volume, and the temperature, the A constant and the B constant for CO2. Ideal gas, pressure is just going to be, put those in, solve for it, I get 102 atmospheres. If I use the van der Waals gas, plugging in the numbers, man, it looks messy, but if you keep your head about you and be careful, you would solve for 62.4 atmospheres. Typically, the real gas is going to have a lower pressure than the ideal gas, and that would be a way to double check yourself to see if you've made one possible mistake would get a pressure greater than the ideal gas pressure. Okay, here's a checkpoint on this, and you can work through that. Be sure to work these out. If you need any encouragement, look at the practice quiz and the practice exam. All right, so this concludes everything that I need to do for this lesson. I see that some of you were able to stay around. I appreciate you being here at this time, but let's all go to supper. All right. Y'all have a great weekend, and I'll see you again on Monday.